How's it going, guys? Welcome to another Soul Encoded tutorial. Today we're going to go over closures and recursions in JavaScript.
Have you ever wondered what it could be like? And now it's all said.
In the last tutorial, we're talking about various aspects of function. I hope you guys are able to complete the first two set of challenges for this particular functions write-up, and you guys are ready to move on for closures and recursions. Now remember that closure and recursion is one of the most commonly misunderstood topics in programming. But don't worry, we'll break it down bit by bit, line by line, and hopefully after this tutorial you guys will have a firm understanding of closures and recursions. Let's dive right in to closures first. So remember that closures in the simplest form is just a function that wraps another function around it. But there's a few interesting things that happen when you wrap a function around another function. I think for the topic of closures, there's a guy named Kyle Simpson. He's one of the, I would say, prominent JavaScript advocates. His definition of closure is probably one of the best. It's very succinct. So he says closure is when a function is able to remember its lexical scope, even though that function is executed outside of that lexical scope. It's a mouthful, but I believe a pretty good definition of what closure is. Now, what is lexical scope? Lexical scope is just another kind of fancy way to describe what you have access to in your current scope. So let's write a quick example to describe this. Let's create another add function, but this time let's use closure. Var summation equals function. We'll pass in a value, or let's pass in the total. This is like the same, but let's just pass in the total. And in here, we'll create an inner function, func. And here we'll pass in the value that we're going to add to the total. So we'll say total plus equal value. Let's log this total here. And then let's return the inner function here. So the summation function will basically return the inner function. And down here, so now we have a completed function. Now let's invoke. Now let's assign the summation invocation to a variable. So we'll say var adder summation, we'll just say 0 for now. We'll give it the initial value of 0 for total. And then now we could call adder 2, for example. So let's give that a try. It printed out 2. Now let's invoke that same function one more time and say 4. And if we did this correctly, this should be 6. 2 and then 6. I printed it out twice. So why does this happen, and why is this important, and where is the closure happening? What is the lexical scope? Let's go over that bit by bit. When you look at this entire summation function, this is just a function that wraps around another function called the inner function, right? Now notice that we have a value called total being passed in as an argument. Now remember that when you pass in an argument, it creates a variable called total in this function scope right here. The inner function has access to this total variable, and that's why we're adding it here. Total plus equal value. Now the value is something that will be passed into the inner function later, right? And so all this is doing is keeping this total in the summation scope, and then is adding it to that with the new value that is being passed in. So down here, var adder equals summation 0. All I'm doing there, I'm doing two things. I'm passing it a value of 0. I'm also invoking the summation function. Now that invocation actually returns the inner function, as you can see on line 8. So the lexical scope of that particular inner function is the value total, the variable total. Even though this summation even though this summation function has been already invoked and it has finished invoking, that total variable still exists. That's kind of what we're looking at. And note here that adder2 maintains that status, and then when you add adder4, it adds to the 2. That total value does not get rewritten. So that's kind of closures in a nutshell. Oh, before I move on, let me talk quickly about what IFEs are. IFEs are spelled like this. It's immediately invoked function expressions. That's what IFEs stands for. And all it is this expression up here, the function, this whole thing right here can actually be invoked right away by adding curly braces right there. And what this does is now we don't need this particular adder, like assignment of the invocation. Once we do this, let's not forget to add the 0 because we're passing it an initial total value. These adders need to be summation as well. And then when we invoke it, we will get 2 and 6 as well. But yeah, so that's closure in a nutshell. So let's move on to recursions. So I think recursion is one of the most simplest concepts to understand, but it's actually really difficult to solve problems using recursion. At least for beginners, it's just one of those concepts. Unless you have like a strong math background, the concept of recursion is actually kind of difficult to wrap your head around. But I'll give you a few tips. Let's first define what a recursion is. All recursion is when a function calls itself over and over and over. Tip number 1, you want to think about the base case first. At some point, a function needs to end that recursion call, right? There's got to be some state where it's like, okay, I'm done calling itself. If it doesn't, you'll have an infinite loop where you just keep calling yourself over and over, and then you'll max out the stack call, and then your program will break. Base case is basically telling the program, hey, for this particular case, this is when you stop the recursive call and then start returning the values back up to your stack trace. So that's the base case. So think of the base case first. The second thing to solve the recursive problems is think about the smallest problem that's not the base case. The smallest problem. Like, let's take this factorial problem that we have. Let's look at this factorial problem. Let me copy it over. So let's explain what the base case is and what the smallest bit of the problem is, right? So looking at this, if you look at this if statement block right here, if n equals 1, and if that's true, return 1. So that's the base case. Why is that the base case? Well, that is essentially like the first step, right? Like, let's say that you're trying to figure out 5 factorial. The very first step to figure out is what is it at value 1. So that's why that particular value is 1, because you can't go any below that base case. Usually figuring out the base case is pretty easy. The next hardest part is actually figuring out the second part, the algorithm itself that you need to call multiple times, the recursive portion. That's actually more difficult to find. For the factorial part, let's think about the factorial of 2 will probably be the next step that you should look at. So let's think of 2. You say, okay, I take my current number, which is 2, and then I need to multiply it by the number that came right before it. So that's n minus 1. So that's your algorithm right there. If you look at it, line number 5, it returns n times factorial n minus 1. So the factorial portion is calling itself again, and that's the recursive part. And the n times factorial n minus 1 is the algorithm. So the way this function works is you call factorial 5, and then it will go through this base case. It doesn't meet it. So it'll say, okay, 5 times factorial, and it calls itself again, 4. Like 5 minus 1, which is 4. And then it goes through that again, and it keeps looping over that until it hits 1. And when it hits 1, then it will return this value as it hit that block, and then it will exit that call stack, and it will never call that recursive function again. So basically it will return 1, and then that return will return the basically call, the factorial call that it called, and so forth until that particular value is returned back all combined. And that's essentially how recursion works. One thing to note is that any recursive problem you could probably solve iteratively as well, but sometimes recursion problems are much more elegant and simple to reason about. It's not necessarily faster usually, but it can be a lot easier to write certain things in recursion. So what are some things that you would use recursion for? Anytime there's like a tree, it's great to use recursion to be able to look through the entire tree to, you know, grab all of like whatever elements that you need. So in the web, we have a DOM, which is document object model. And that all that is just a tree of all of our HTML tags. Basically, every time you do like get query selector, all it's doing is going through the tree, finding all the instances of your class name, for example, and then making the programmatic changes. So, and recursion is used there. That's pretty much it. So that's it for recursion. Let's quickly move on to explaining what the challenges are, and I have a few like kind of announcements in regards to like this topic. Always be closuring. That's the name of the first challenge.
Always be closing.
There's two challenges in this overarching challenge. The first one is a very common like interview question. People will test you on this to see if you understand lexical scope and how closures work and how like the whole variable hoisting kind of thing. So yeah, it's just a for loop with a set timeout, and then you would think that if you log the set timeout, you would think it would print out like 1, 2, and 3, but in reality it prints out 3 times. With your knowledge of Clojure, you should be able to figure out why this is happening, and a hint is if you use an IIFE, you could kind of fix this problem. Yeah, just make sure that you could print 1, 2, 3 while keeping that set time. The other one in that Clojure problem is another adding function. Basically this one you create like a base number as a default and then you add to it. It's very similar to the example that I showed you, but it's slightly different. So look out for the differences there. In the recursion world, I created the most common recursion problem, I would say, which is the Fibonacci sequence. It's just a mathematical sequence. All it is the nth value is the summation of the previous two numbers. But yeah, that's pretty much it for this lecture. So now like a little bit of side thing, I'm going to start probably doing like HackerRank problems. I feel like I need to have more challenges, especially in JavaScript for you guys, you know. And recursion, like going through this recursion problem, I realized that like I need to show you guys more problems. And I feel like HackerRank has a wealth of like good problems to solve. So I'll probably kind of stream what I'm doing and explain what I'm thinking while I'm solving these problems, and it will give you more chance to like practice these problems. Anyways, I hope you guys enjoyed this video, and next week we're going to be covering data structures and like other like various JavaScript like helper functions and things like that, and the JavaScript object and things like that. So yeah, look out for the next video, and I hope you guys have a great rest of the day. Bye.